Right, okay, in the second part of the talk, I will try to talk about Beer's idea of the proof of Thurston's classification of alternatives of surfaces, and in the second part I will talk about, well, certain hyperbolization theorems, okay? And yeah, let me quickly remind you that, okay, like what we did in the first part, we introduced the technical space of a surface, well, possibly with punctures, as a space, like of all possible conformal structures on the surface up to natural equivalence relation. And well, the last thing, well, maybe not the last, okay, but one thing that I said that, like there exists a natural action of the mapping class group on the technical space, which is given essentially by the precomposition. So if I have a point x phi, then I could precompose the corresponding marking map phi with f and get a new point in the technical space. One thing that I want to know that for the new point in the technical space, you see, so you do not change the Riemann surface. The Riemann surface remains the same, right? But what you change is the corresponding marking, so you change the formula. So that will play a role later on.
But also maybe Misha, just to I'm asking the same again, but are you saying that if you have a complex structure on a surface, it has no, wait, what am I saying? There's no element of the mapping class group that will map it to itself? I mean, so there's no stabilizer?
No,
there is a stabilizer?
There are possible stabilizers.
Yeah, but then I am still confused, right? Because then, right, this phi does have some sort of isotropy, right? Like certain things are fixed by this Muller. No, wait. No, I'm confused. What? No, okay, I'm happy. Sorry, yes, I'm happy myself.
Okay. The speaker is always happier, nobody else managed to answer the question. It's always good. All right. So, but one thing that we need to talk about the first. We need to talk about the metric of the technical space. And to define this metric, we need to quickly talk about quasi-conformal maps. So suppose that I have some two surfaces x and y, and I have some smooth map between them, well, except maybe outside maybe except finitely many points. Then we could write down the differential of the map h with respect to the z coordinates. So using the vertical derivatives. So I will have the hz and hz bar. And not particularly that hz bar is equal to 0 if and only if h is holomorphic at a particular point, right? And what I want to look at, the ratio between hz bar and h of z at each point. And one quick remark that the map is rotation preserved if the absolute value is less than 1. And now with this in mind, what I want to define, okay, suppose I have some orientation preserving smooth map between the two Riemann surfaces. I define the dilatation of h at some point p as this ratio. And the way you should think about this as follows, it's a very, geometrically that's a very easy thing. So your map h locally maps, so to say, infinitesimal circles to infinitesimal ellipses. And this key edge, that's exactly the ratio between the two axes of the ellipse. Okay? So you have some smooth map, it maps infinitesimal circle to infinitesimal ellipse, and you look at the ratio of the corresponding axis, and that's what you call the dilatation. And well, the dilatation, so that's the dilatation at the point, and if you want to talk about the dilatation of the map, you look at the supremum over all possible points where the map is differentiable. And the map is called quasi-conformal if the dilatation is finite. Put it differently, your map is not allowed to distort, circles too much. So there should be a uniform number k so that H is not allowed to stretch your infinitesimal circles too much. And a quick remark, if you have two quasi-conformal maps, then the dilatation of the product, as you could sort of say, imagine, is actually submultiplicative. So it's less or equal than the product of dilatations. And with this in mind, we can actually define a metric on the Teichmüller space. Suppose that I have 2 points in my Teichmüller space, tau1 and tau2. So I have two Riemann maps. Sorry, I have two Riemann surfaces, x1 and x2. And I have two corresponding markers, phi1 and phi2. So what I want to do, I want to find a QC map such that F1 composition with H is isotopic to the other one. And I want to look at the infimum of the log of the dilatation over all such H. So put it differently, what are the H's that you consider? You consider the composition of F phi1 inverse phi2. So that's some homomorphism up here. You can make it smooth, and you look at the minimal possible dilatation of this one. Okay? And so that's the and the claim is that actually this distance defines a metric of the Teichmüller space. So let's quickly think about it. So, it's almost obvious that this is symmetric. The triangle inequality follows because you have this submultiplicativity, and that's actually the reason why we take log. So so we have a quantity that is submultiplicative, but for the triangle inequality we want to have some additivity, right? So for that we take the log, and that's why you get triangle inequality. And the distance of a point itself, that's exactly how we set up the equivalence relation to Teichmüller space, right? So if you have the distance is equal to 0, it means that the corresponding k dilatation is equal to 1. So, and if the dilatation is equal to 1, it's actually, it follows from Weil's theorem that your map is bihomomorphic. So your map is if you have a homomorphic map H, that means that x1 and x2 are equivalent to the Teichmüller space. And also a quick note that it automatically follows essentially from the definition that mapping class group acts by isometries, because what does mapping class do? Well, it's essentially precomposes with F, right? But if you want to look at the distance between the corresponding images, it's very easy to see that you have a reconstruction, meaning that if I have 2 points tau1 f and tau2 f, I look at the corresponding distance, then this distance is less equal than the original guy. But because of this, and since you could look also at f inverse, you also get the other inequality for free. So therefore, you actually have isometry. So what's important that the mapping class groups acts on the Teichmüller space by isometries.
Can I ask, so I have a bit of I don't really understand maybe the notion of this quasi-conformal. If I take a smooth map, a diffeomorphism, then it's automatically quasi-conformal.
No. I mean, this supremum.
Yeah, if the manifold is compact or something.
Yeah, you can find. So I mean, okay, if you have a compact thing, then you take a supremum over compact thing, so yes, you'll find it, yes. Yeah, but potentially, if you have, let's say, infinitely many punctures, that's not for sure. Yes. I mean, if you have infinitely many punctures, then you could actually always find a QC representative.
Sure. But maybe, so this dilatation, for homeomorphism, it's not even clear that this quantity is well defined. No, because
Yeah. Well, then you do need to have some smooth structures. Yes. So that's why it's set up.
Okay.
I mean, there is a different notion related to this, which is called quasi-symmetry, but this is like a more native notion. It's at least here,
Okay.
that's not so much relevant for the discussion that I want to have to do. Yes, so yeah, let's go back to this thing. Yeah, so again, let's look at the Beer's theorem. So I have some automorphism F. I look at the translation length of the induced action of F on the Tachmiller space, and then there are these three cases that distinguish the type of your automorphism. What I want to say. Okay, in the first case we could actually be really precise, and that's a very easy thing to prove. So let's just quickly talk about the first case. In the first case, you have the translation length equal to 0 and is realized, which means that you have some point tau in the Tachmiller space so that f applied to tau is equal to tau. But what it means essentially by definition, well, it means that you have some conformal automorphism of X that makes this diagram complete, so that phi composition with I is isotropic to this guy. So that's just tracking out the definitions. So this guy is exactly the map up here. So this is the image of tau times f. Well, but this should be equal to tau. It means that there exists this conformal automorphism I that makes this diagram complete. But now because X, well, is a Riemann surface and X is an automorphism, we know that in this case X has to be of finite order. So if if you're not in the station of the torus, then the automorphisms of the Riemann surface would have some finite order. In particular, it means that my map F is isotropic to some map, which is given by this conjugation. Well, but this guy is then of finite order, and that's it. So F is isotropic to the map that is periodic. And now that we showed actually something stronger, we show that this map, within the isotropy class of F, there exists a map that preserves some conformal structure given by this term. So that's the proof in the first and the easiest case. The other two cases are much more involved, and I will probably say just a few words. So the second case tells us the following. Suppose that the infimum is not realized, then we need to construct some. Suppose that the infimum is realized, but the translation length is positive, and then we need to prove that f is pseudo-Nosov. So the crucial thing up here is that there exists a very natural way to describe geodesics within the Tachmiller space. So geodesics within the Tachmiller space are described using the so-called Tachmiller map. So remember that we've been looking at the distance between 2 points in terms of the infimum of the log of the dilatation, right? And the natural question that you could ask, okay, it's an infimum of H, of the quasi-conformal map H. But is there a map H that gives you the infimum? Right? So is there some quasi-conformal map that delivers the minimal dilatation? And the answer is actually yes. So there exists a special map which has, a very special structure. So there exists unique, this has some special sense, map H such that the dilatation of this guy is less or equal than, you know, like the rotation of any other guy. So where, you know, H and H prime, you know, like are two maps between the Riemann surface. And this map has a very special structure, so you can put two quadratic differentials on x and y. These quadratic differentials define the foliations, and then what H does with these foliations, well, it should preserve these foliations, except that, you know, like it stretches the horizontal foliation by factor lambda, let's say, and it contracts the vertical foliation by lambda. So this Teichmüller map that delivers this infinitum, it has a very special form that already includes some foliation. And essentially the geodesics in the Teichmüller space are constructed by varying the conformal structure in terms of this contractional expansion factor lambda. So when you vary this lambda, you get a line in your Teichmüller space. And that's more or less how this second case is being proven. So you show that F should preserve some geodesic, but if this is the case, so if F is realized, then it should preserve the geodesic that connects. So if infinitum of tau and infinitum between the distance of tau and sigma of tau is given by, well, some particular point, then if you look at these 2 points, and well, we know that this guy is positive, so you will have 2 points tau prime and sigma of tau prime on the Teichmüller space. So this defines you a geodesic within the Teichmüller space, and you show that the map F, so the action of the map group by F, so it preserves this geodesic. And preservation of the geodesic actually means that the corresponding foliation should be there. So that's how you construct the pseudo-message structure. So again, like if you want, I could look into the details, but maybe that's too much if you want to talk about.
Maybe can you at least say a bit more about how geodesics correspond to
yes, sure.
or stretching?
So I could say some more words about this. So if you have a point tau in the Teichmüller space, okay, and and you have some quasi-conformal constant k, then, well, let's say that you have so then, you know, like you have this unique guy that realizes the corresponding dilatation.
Okay.
And so H is a QC map, and it has a very special structure. So you have some foliation here,
This is one foliation, or it's the pair you had before?
So it's a pair of foliations. It's a pair of transverse foliations such that H preserves these foliations and it spacious one and contrasts the other one. Okay. So now.
Also, maybe just to clarify one thing. So, the foliations, they are related to the conformal structure because they're kind of like paired by J in some sense, or
so they are related somehow, but you know, like, but in this terminology, you just have, well, like some quadratic differential on this Riemann surface that defines you the corresponding horizontal vertical foliation. You have another quadratic differential that defines another foliation, and H respects both of these foliations. So it maps them invariantly. Okay. So now what you can, yes, and what does it mean that it depends on the invariant radius? So you have well, like so I mean, similarly like to the pseudo-analysis thing, you know, like you have lambda contraction in one direction and lambda stretch in the other one. And then, you know, like if you fix your quadratic differential on x1, which is given by this guy, what you can do now, you can vary the corresponding contraction factor. So you have one lambda that is coming from this point x2, but now you can vary it continuously. And this defines you a new Riemann surface, and this Riemann surface would, so this Riemann surface would exactly correspond to the geodesic that connects x1 and x2. So now if you have these special points, you know, like tau 1 and sigma of t, well, like, okay, the thing that delivers you infinity here, you have this geodesic, and you can show that because it delivers infinitum, f has to leave the geodesic invariant. And since f leaves the geodesic invariant, it preserves the corresponding information. So that's the idea. I mean, those are the details that maybe I want to okay, maybe let me still spend 5 minutes on the last case, on the case when you're not realized. So in the case when you're not realized, so what does it mean? It means that, you know, you have a sequence of points tau n in the triangular space such that the distance from tau n and sigma tau n converge to the sigma of f, right? But the infinitum is not realized. So you could construct a sequence that converges to the corresponding infinitum, but this guy is not realized. If you have such a situation, if the infinitum is not realized, then if you look at the corresponding projections in the modular space, so remember, we had a Tachmann space, right? And there was a space of modular space, a space of Riemann surfaces. So we could project our points in the Tachmann space to the modular space. And now the claim is that if this infinitum is not realized, then these points have to diverge in the modular space. So that's something we need to prove. So claim pi of tau n diverge in the modular space. So that's something that you can prove well, quite easy using again the definition of some compactness arguments. But now, if you have a sequence of points that diverge in the modular space, remember the modular space consists of the Riemann surfaces. What it means? It means that this Riemann surfaces up here should develop arbitrarily short geodesics. So the Riemann surface at some point should become very, very thin. Okay? So this means that if you look at, let's call it alpha of tau n, so it's the infinitum of the length of the corresponding curves in the surfaces of all gamma is simple possible. So I want to look at the length, at the minimum possible length of the geodesic. Okay? And I claim that this guy has to go to 0. Or put differently, the log of this guy should go to minus infinity. Okay? But now the crucial idea, which appears like also in the theory of rational maps, is the following. Suppose that you have one Riemann surface. Then there exists a universal number of geodesics that can be smaller than some given number. So it's just, so like if you have, there exists some constant k, there exists constant p such that only finitely many and finitely many in the uniform sense of geodesics in K can have lengths less or equal than K. So you should really like think about this in the following way. You know, like you have your Riemann surface, and then there are like some thin parts which gives you this thick, which gives you this short geodesics. But then, you know, like all other simple closed curves, they would have to cross through these thin parts, but that means that they pick up large hyperbolic lengths. That's the idea. So if you have some thin parts, so if this is small, and you have, you know, like some geodesic that crosses this thin part, it have to pick up some large lengths. And because of that, essentially, these geodesics, they actually do not cross. So if you have two small geodesics and small is a quantitative statement, then they actually cannot cross in the Riemann surface. So now if you have such a situation, if you have, you know, like log of your length of your geodesics goes to minus infinity, it means actually, you know, like that in the spectrum of the length of your geodesics, you should really, you know, like go to minus infinity, but there exists this universal bound log k, which tells you that only finitely many guys could live, you know, like to the left of this thing. Well, but we know that, you know, like this guy is a divergent to infinity, so therefore it means that we should have arbitrary large gaps when no elements of the spectrum appear. So there exists a portion of some real line which does not give me the log of the corresponding geodesic. But now, you know, like what you can do by taking some sufficiently large gap, you know, like you could start with some curve gamma and iterate it using this sigma f map, and it has to stay within this arbitrary large gap. So like it can. So if you apply the sigma f, they actually do not move far in the tabular space. Therefore, the images of this curve gamma, they would stay within the same, within this, you know, like this arbitrary large gap. But this means that this curve has to be periodic. So we know that, you know, like there are at most, whatever, 3g minus 3 curves on the Riemann sphere that are disjoint. So therefore, you have periodicity of some curve, and that means that you have reducibility. So you have a curve which is periodic under the Laplace pattern. So that's the idea behind this reducibility part. So you show that, you know, like you have some invariant curve by first observing that you have divergence as a modular space. Divergence as a modular space implies that arbitrary short geodesics should develop, but if arbitrary short geodesic could develop, thanks to this gap argument, they could actually show that there exists some invariant curve. So that's like the key points of this argument. Yeah, sorry, I think it was like too condensed, but yeah, if you have questions, maybe, you know, maybe add some details later.
Maybe we should answer
Yes.
a quick question. So it's also kind of like the intuition for 3 that kind of, if you were to really kind of go to kind of to some compactified version of the moduli space where these things have really collapsed, these are your pieces of your reducible pieces, right?
Yeah, so like there exists this Markov-Dirac interpretification, yes, so like of the modular space, and that's exactly when you collapse some curves. Yes.
And okay.
Yes, and this is exactly the natural interpretation.
No, but so and it also really corresponds to the reducibility, the composition of.
Yeah, like you could say that like there exists some stable curve in this.
Okay.
Okay, I mean, if you use this kind of Thurston's kind of argument, then you actually can exactly reconstruct the corresponding reducible point by looking to each point in the
Okay. Yeah. Thanks.
So that's the automorphism piece. So now let me talk a bit about the three manifolds piece. And here I think I'm just going to use the blackboard completely. Yes, the version of the so Thurston proves the following statement. So Thurston proves the following statement. So every closed irreducible and a toroidal manifold is hyperbolic. So let me try to quickly explain the notions without going into many details. Irreducibility means that you do not have essential spheres. Toroidal means that you do not have like essential tori. You have to be careful how to define this. But okay, let me just debate and say that you do not have essential tori. What does Haken mean? Haken means that your manifold is not too simple, so it means that you have some incompressible surface inside it of genus of these two. So that's what Haken means. And if you have a Haken manifold, then essentially it means that you could build up you could build up a Haken manifold essentially by gluing a hyperbolic polyhedron. So there exists this Haken hierarchy. If you have, an incompressible surface, you can cut your surface along. If you have an incompressible surface inside your free manifold, you can cut your surface along this incompressible surface. Then you can cut your manifold along the surface, and then you have either one piece or two pieces, and then you can continue this process. And you stop once you just have pieces that are homeomorphic to the three balls, and then you put hyperbolic structure in three balls, meaning that you have some hyperbolic polyhedra, and then what you want to do, you want to glue this hyperbolic polyhedra together to get a hyperbolic structure on the final thing. And that's essentially how the proof of Thurston works. So you have your Haken hierarchy, you start at the lowest level where you have just balls, and then you want to explain how they actually glue hyperbolic pieces together to get a new hyperbolic manifold. And that's actually not so easy to do well. So there are several important ingredients in this step. So in particular, there exists some orbifold, some step which is called orbifold trick that I'm not going to touch at all. But what I want to talk about is the so-called final gluing step, which is described by the following situation. So I'm going to just restrict ourselves to a very special situation. So suppose M is a hyperbolic three manifold. Okay? And let's suppose that it has exactly two boundary components. Suppose boundary of M has exactly two boundary components. And let's suppose that they are homeomorphic to each other via some involution, orientation versus involution. So how you should think about this is exactly this final gluing step. So you have some closed manifold, you have this incompressible surface, you cut it out, And then, well, okay, in this case, it's split your manifold into just one piece, but you have these two boundary components, and now you have a hyperbolic structure on M, and you want to glue this back in together so that you have a hyperbolic structure on the good manifold. So that's a final step. So we also have orientation, reversing, involution, I from S1 to S2, and this is the glue net. Okay? And now what I want to do, yes, so I want to glue my manifold back in and say that, well, I don't know, need to show that the glued manifold admits a hyperbolic structure. So that's what Thurston does. So he shows that the glued manifold admits a hyperbolic structure. And how can we do this? And that's exactly the part where the technical theory comes to game again. So the crucial part of the theory due to pairs again, that if you have M geometrically finite 3 manifold, then the space of all possible hyperbolic structures that you can put on M is isomorphic to the Teichmüller space of the boundary of M. So how you should think about this? So you have a geometrically finite 3 manifold, which means in particular that you have finitely many boundary components of M. So let's say that delta M has just 2 boundary components. And then this theorem tells you the following. You can just put some conformal structure on each boundary component, and this determines uniquely a hyperbolic structure on the whole manifold. So this is the whole so-called Beer simplification.
But so probably there are some hypotheses that are not mentioned, because what if I have my manifold which has no boundary?
Then you have most of rigidity.
Okay.
If you do not have boundary, it tells you that it exists on one conformal structure.
Okay.
And this is exactly most of rigidity. Yes. So, what do we do? What do we want to do now? So that's the Beer's theorem, okay? And now I have this gluing part. Yeah, I want to examine 20 some minutes talk about this schema and this very special station. So suppose gamma is a Kleinian group given the hyperbolic structure on M.
Lisa, maybe one question. I mean, because like I'm right confused, because you could say, well, if you're like in this kind of final gluing situation that you said, you would say, well, if I had put the same structure I can glue, and that by that theorem, whatever fills it is unique, and if I put different stuff, it's just different, then I'm sad.
So putting the same thing is not good enough, right? because there exists this map I, right? So you have this involution, right? And the
Right.
structures should match after this involution.
Oh, I see.
Okay?
But what if you put one on the one acted by involution, like by the gluing that you want? Maybe I'm confused about what you want.
So, okay, you're absolutely right, yes. So I want to put some conformal structures on the boundary so that they would, so to say, okay, like, that's not 100% correct. I want to, so to say, put this conformal structure so that I could then put this back in together. So how you could imagine this, you look at the tubular neighborhood of the surface and then you want to put them together by an Amazon.
Yeah.
Okay, so that's exactly what you want to do.
Yeah.
Like the right question, so okay, the right setup up here is that you need to get this conformal structure that would be respected by this involution hash.
Yeah.
And that's what I want to describe how do you get it. Okay?
I mean, so because it's also kind of important how the whole structure is arriving to glue
Exactly,
in a
yes,
hyperbola
yes,
way.
exactly.
Okay, so
Yeah.
I understand what you're doing. Okay, more or less. Okay, I think I'm happy.
Well, so okay, maybe let me just take like the easy situation. The easy situation is like this. Suppose it like a fixed surface S, and then you look at the interval bundle. Okay, and your gluing map is just some element of the mapping class group on S. Okay? And now indeed, you want to put some conformal structure up here, so is that, if you apply F, you want, so to say, to get back the same structure so that you can glue this back in. Okay? So the detail up here, is that, you have this map F. And in particular, this actually situation, when your map is an interval bundle, so when the manifold is an interval bundle, it actually has to be considered separately. And in particular, so that's another kind of hyperbolization theorem due to Thurston. So he shows that you could actually glue this thing together and get a hyperbolic structure if and only if F is pseudo-isotropic.
Okay.
So that's like another theorem. So like, okay, if here you have genus of these two, you have some pseudo-isotropic converse in phi F, then you have a hyperbolic structure on this mapping torus. Okay? But that's like a special station. In general, your manifold may have two boundary components but may not be neutral boundaries. So there are like these two different situations. And they're actually distinguished by the corresponding Kleiner group. Yes, so in particular, okay, let me just try to say things quite quickly. Yeah, so like we look at the Kleiner group that defines the hyperbolic structure on M. So then we look at the corresponding regular set of this Kleiner group. So if we are in the considered situation that the regular set of gamma would be a Sierpinski harmony. So each component of sigma of gamma is some disk, and then the quotient of this disk by the action of gamma by the corresponding stabilizer. So you look at gamma, you look at the stabilizer of this disk, and the quotient of this disk by the corresponding stabilizer. So this gives you essentially one conformal structure on the boundary component. So that's how you should think about it. So, okay, did I lose you completely at this point?
Me, yes.
Okay, maybe let me do slightly more careful version of this.
I mean, so
So
in this case,
gamma is a discrete subgroup of ESN to C, right? So it's a group of Möbius transformations, okay? And this group of Möbius transformation, okay, it acts in the interior of the hyperbolic wall, but it also acts on the boundary, okay? And the action of the boundary gives you the regular and limit sets. So what is the regular and limit sets of a planar group? The limit set lambda of gamma is relevant, is the accumulation set, let's say, of some orbit of the group. So those are actually the pictures of limits. So this is how, so in white it's a limit set, in black it's a regular set. Okay? So now if you look at the quotient of H3 union delta gamma by gamma, what you get essentially manifold union with its boundary. So the quotient of H3 by gamma would give you the interior, and the quotient of delta gamma by gamma would give you finitely many Riemann surfaces that are on the boundary. Okay? So that's what you should think of. In the geometrically finite case, you have finitely many Riemann surfaces on the boundary. Okay? So now, I want to tell you how, by picking, let's say in this case, remember that in our station, delta M has two boundary components that are identified by some involution I. So I want to tell you how one can define a map from the Teichmüller space of S1 times the Teichmüller space of S2 to the Teichmüller space of S1 bar, which is S1 with like the opposite orientation, times Teichmüller space of S2 bar. And this is the so-called schema. So if I have some point up here, so I have some Riemann structure here, x1, I have a Riemann structure x2 here. Remember that, like by the burst identification, if I have a point in the Teichmüller space of the boundary, I have the corresponding planar group. So I have this planar group gamma, and well, for this planar group gamma, I have that the conformal structure on the boundary is given exactly by x1 and x2. So now what I can do, I can pick some disk, let's say that corresponds to x1. So x1 is given by the quotient of this disk by the stabilizer of this disk in gamma. And what I can do, I can look at the complement of this disk. And I can quotient out the complement by the corresponding stabilizer. What I will have some Riemann surface, but this Riemann surface lives on the S1 bar. So it's a conformal structure on the complementary part, so I have the reverse translation. And I can do exactly the same thing for S2. So I pick, like some component that correspond to x2. And I look also at the conformal structure of the complement, and this gives me Teichmüller space of S2 bar, and this is a scheme in my S. And now the Thurston, the pullback map that is of our interest is the composition of S, well, with the involution on the boundary defines the identification between the corresponding Teichmüller space of S1 and S1 bar. So I can look at this composition. So I have this scheme map times the corresponding map induced by the involution, and this is the map sigma of our interest. So remember I told you that in all the situations
We did this earlier as well.
In all the stations, we have a map sigma from one tactical space to another tactical space. And in this case, this is exactly the map that is of our interest. And having, so, and if you want to glue back manifold, you want to find a fixed point of this map. Again, so geometrization is related to a fixed point of sigma. And geometrization, in this case, is related to the fixed point of this point. And now the crucial thing, what Thurston shows. So he shows that, so this I star, so that's just isometry. So it's just the corresponding map of the tactical space that is used by evolution. So this is isometry. So whatever, you want to do should be controlled by the skinny map. But now, if you have this Haken situation, then this map X is actually contracting, and it has bounded image. So that's what Thurston shows. And because of this, so since S is contracting, you can run a fixed point. Well, essentially, you could just run the iteration of sigma, and it will converge to a fixed point. And that's how you show that the fixed point exists. Existence of fixed point of sigma follows from contraction of S. And maybe two remarks that I want to make at this point. Well, remark number one, S is not always contracting, so for map S to be contracting, you exactly need to exclude the situation that this Haken manifold fibers over a surface. You have to exclude this interval bundle stage. Because you can show that actually S is contraction if and only if M is not an interval bundle, and if it is, then it's actually isometry. And of course, if you have an isometry, then you are in a bad situation because this isometry, so would essentially mean that if you want to iterate sigma, okay, you iterate isometry, and you would diverge to the bundle. And that's kind of another part of this whole machinery. So that's a special case of the interval bundle. So the case when your manifold fibers over circle, and this requires a special treatment. But otherwise, if you're not an interval bundle, we can use this fixed point kind of argument to construct this fixed point, and then we can glue. And again, I want to emphasize with some keywords. The fact that you could glue back manifold in together, that's also a non-trivial step, and this is a so-called Klein-Masket combination theorem. So there is a specific theorem which tells you that if you have this nice fixed point, then you could actually glue manifold back in together. And what we reckon, so what do we get at the end? We get a manifold with the same fundamental group and some hyperbolic structure. And again, there exists some rigidity result which says that if your fundamental group is the same, then actually your manifold is homomorphic to the original one. So there exists this kind of final little piece. You reconstruct some manifold, okay, but how do you know that it's homomorphic to the original one? Well, the answer to this is because you can control the corresponding fundamental group. You can say that the fundamental groups match. And then you could say that actually they are polymorphic. So maybe let me stop the discussion here, and I will be happy to answer questions of more details depending on where you want to go.